The reason there is weather on our planet is that the Earth is round, so the sun heats it unevenly, and that sets the air in motion.
But the Earth also spins, and this spin shapes the patterns of weather we observe. As you now see, when things are spinning, it's a pretty complicated world. And while we don't notice it, here in Pennsylvania, the Earth is spinning eastward at 700 miles per hour.
Yes, the spinning Earth is a dizzying place, and from where you're now sitting, you've just gotten a glimpse of the forces at work. It is apparent that it's time to consider something we call the Coriolis force.
Global thermonuclear war.
Fine.
All right.
Which side do you want?
I'll be the Russians.
I have 7, correction 8. That's 8 redbirds, 2 degrees past apogee.
Better get the old man down here.
Overday, we have Soviet missile warning. Check for malfunction and report competent.
The Coriolis force does not only affect the weather. In fact, the forces of spin must be considered when missiles are launched from one part of the Earth to another. The Coriolis force is important for any motion in the atmosphere that traverses long distance or takes a long time. If the Earth were not spinning, the air would flow directly from the heated equatorial regions to the icy polar caps. However, these satellite pictures from Japanese television show that in the middle latitudes, weather systems generally move from west to east. This motion is a consequence of the Coriolis force.
We've come to the local playground to be able to show firsthand just how this Coriolis force works.
That's right. This merry-go-round is going to eventually play the part of our spinning Earth, and this baseball here will be a chunk of air. Now here in this non-rotating world, if I roll it to Paul, it goes straight.
I roll it back to Fred, also goes straight. Isaac Newton long ago said in his first law of motion, an object going straight will continue going straight unless it's acted upon by a force.
That's right, but if we were to set this merry-go-round rotating, it would be a whole different world. Would you do the honors, Paul?
My pleasure, Fred.
Well, thanks, Paul, for the spin, and welcome aboard our private rotating world. We're going to try this rolling the ball trick again, and now we're pretty good at rolling curveballs.
That's right, Fred. You can see that each time it's deflected to the right, which is exactly what happens to all air motions here in the Northern Hemisphere.
That's right, you know, and it wouldn't look quite the same if we weren't on this merry-go-round. Let's take a look at how this looks from above.
From up above, the ball is and continues to go straight between us, meaning that the Coriolis force only needs to be considered for those who are rotating. On weather maps, the motion of air around lows and highs is subject to this Coriolis force. Air flowing from high to low pressure, when deflected to the right by the Coriolis force, takes on the familiar clockwise rotation in this hemisphere. By the same token, air moving toward the center of low pressure, being deflected to the right in the Northern Hemisphere, takes on a counterclockwise spin.
If you've ever wrestled with one of these babies, a revolving door, you know that rotation can interfere with your motion. And so, too, it is true of the Coriolis force. The Coriolis force in the atmosphere interferes with the direct transport of air from the equator to the pole. And in so doing, it helps give the size, the shape, and the intensity of weather systems we observe. However, unlike in this revolving door, in the atmosphere, there's simply no way out.